Welcome to Spring LIB.
Our question says that for a given wavelength of light, what is the minimum slit width for which there will be no diffraction minima? And this is part A. Okay, well, in a diffraction pattern, the minima occurs when d, the diameter of the slit, times the sine of the angle of diffraction, theta, is equal to m times the wavelength of light, lambda. Where m here is the order of diffraction. So it can be 1, 2, 3, 4, 5, and so on. It just can't be 0. It's just some integer number, 1, 2, 3 on up. So diffraction minima cannot be observed when the angle for the first minimum is greater than 90 degrees. So we determine the minimum slit width by substituting the value of 90 degrees into the equation. And then this is going to be maximum when the diffraction order is 1 or m is equal to 1. So for part A, based on the situation we're given, theta here is going to be equal to 90 degrees. And we want the first diffraction pattern, so m is going to be equal to 1. So then we can solve for d. And what we have here is d is equal to m lambda divided by the sine of theta. Again, plugging in 1 for m and then 90 for theta. Well, the sine of 90 is 1, so what we end up with here is just simply lambda. And we can box that in as our solution for A. Part B says, what is the minimum slit width so that no visible light exhibits a diffractive minimum? So we don't want any visible light to exhibit a diffractive minima. We already know the situation here. It's going to be when the diameter of the slits, d, is equal to lambda. We found that in part A. So the visible light cannot exhibit a diffraction minimum when the slit width is equal to the shortest visible wavelength. The shortest visible wavelength of visible light is 400 nanometers. So this is true when lambda here is equal to 400 nanometers in the situation that we found in part A. So if lambda is equal to 400 nanometers, that means that the slit width d is also equal to 400 nanometers. So we can box that in as our solution for part B.